On to the fun stuff. So the last couple of classes, we've talked about how to do the power rule. We talked about the product rule and the quotient rule. Pretty much all of those we're dealing with basically polynomials or simple algebraic functions. We did deal with the e to the x in there a little bit, but that's all we basically added in. Now we're going to start looking at some of those other functions. So the first set of functions we're going to look at are trig functions. So let's see if we can find the derivative for sine of x. So without knowing the rule and having the answer, how would we go about finding the derivative of something? What do we get to go back to? What is the definition of a derivative? Right, but there was an actual equation that was the actual what a derivative is.
Equals f of x minus f of a divided by x minus a.
Okay, yeah. Pretty close.
Oh, that one.
You're right. It was basically the same thing.
Oh.
So since we don't have a rule for it yet, we will after I finish this problem. You have to go back to your limit equation. So this one's going to be the limit as h goes to 0 of sine of x plus h minus sine of x all over h. Since I don't expect anybody to have memorized this, the addition rule of trig functions, when we have sine of x plus h, that equals something else. So sine of x plus h. So when you're doing the sum of angles, and ends up equaling sine of x cosine of h. Plus cosine of x sine of h. Yeah. Well, it's not the double angle rule. It's the sum of angles. So it's very similar to the double angle rule because, like, if they were both x's, it would work out to be the same way, which would end up giving you the sum of angle, the double angle rule. But in this case, the angles aren't the same. So, all right. So now I've got the limit as h goes to 0 of sine of x cosine of h plus cosine of x sine of h minus sine of x all over h. So we're going to move these around a little bit. So, because I know somebody's going to ask the question in a second, that came from that and that. Because I know somebody was going to ask that. If I said, "Is everybody good to hear?" So we go, "Huh?" Yeah, that came from those two things. So I basically put them together and pulled out the sine of x. Yes. So sine of x, cosine of h, minus sine of x, right? I pulled out the sine of x. So if I pull out the sine of x of this one, I'm left with cosine of h. If I pull the sine of x out of that, I'm left with 1. Or the other way, if you want to think about it, go backwards. What's sine of x times cosine of h? What's sine of x times 1? So sometimes going backwards, it'll like, oh, that makes total sense. Because like the 1 sometimes screws people up because like, okay, if I pulled it out, why do I need a 1? Well, because if I don't have the 1, you lose that term. And that's a problem. All right. Almost there. So we have this, which we're going to split a little bit, make my life a little easier. So the anything like, does the sine of x, does the limit have anything to do with sine of x? No, there's no more h, right? So I can write this as sine of x times the limit as h goes to 0 of cosine of h minus 1 over h. Plus cosine of x times the limit as h goes to 0 of sine of h over h. Yeah, because they don't have anything to do with there's no h in them. There's no h in it. So that limit doesn't really impact it anyway. It's for, in terms of the limit, it's like a constant. I can just pull it out. So now the only thing we have to figure out is I need to figure out what that is and what that is. And since as of right now, we don't really have any way to do that, let's graph it and see what happens. See what it looks like. See what it looks like it's going to. All right. So we have cosine of x minus 1 over x. Just imagine their h's because I can't put h's into Desmos. What's this graph look like it's going to as it's getting closer to 0? Well, it doesn't equal anything there, but what does it look like it's going to on either side? It's going to 0. So this, that's really 0. Gonna go away for a second. All right, so that's 0. So now let's go back and look at what's the sine of x over x going to. So if we look at this one as it's going to, it looks like it's going to what? Looks like it's going to 1. So that goes to 1. So sine of x times 0 is, cosine of x times 1 is cosine of x. So if f of x equals sine of x, then f prime of x equals cosine of x. Now that you have that answer, you never have to do anything we just did again. It's one of those ones, like if I had just told you sine of x is cosine of x, half you would have gone, great, good, I don't need to, and then I have to go, huh? Why? So sometimes it's good to actually understand like the process behind where this stuff comes from. And that's where that derivative rule really comes into play. Anytime you have a derivative of something you just can't figure out, you can always go back to that derivative rule to use. That'll always work. Sometimes it's easier to use than other times, but it'll always work. So all these other things that we're looking at in the rules and things like this is just things that they've already figured out so that if you know, you can just use them. You don't have to go through and do all that extra work. Yeah.
Will it change if there's different numbers?
What do you mean different
If
numbers?
you put a 3 in front of the x or like a 2 in front of the sign?
No, because if you pull out a constant, you can pull right at the beginning. So then that won't change anything. So we're going to do some of those problems in a minute with like other numbers and stuff. All right. So I'm just going to give you the cosine of x1 and not have to go through all those steps because I don't feel like going through all those steps again. It's the same process though. So the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. So if f of x is sine of x, f prime of x is cosine of x, right? What's the second derivative? Well, the derivative of cosine of x is negative sine of x, right? What's the third derivative? What did I just tell you? The number doesn't matter, right? So if it was a -1, I would just pull it out anyway. So the derivative of sine of x is cosine of x. So this would be just negative cosine of x. What's the derivative of negative cosine of x? Again, the same concept, right? I can pull out the negative sign. So two negatives make a positive. So that's just sine of x. Notice I have now looped. Sine of x and cosine of x loop every 4. So depending on when you had your pre-calc class, when you were talking about complex numbers, if you remember, you had I squared, I to the third, I to the fourth, and then in essence looped, and went right back to I. Same concept with sines and cosines. The derivatives are going to loop every 4. Okay. So that's your derivative one. Sine, cosine, sine of x, cosine of x, negative sine of x, negative cosine of x. And they will just literally keep looping back and forth. That's going to come into play when you look at your integration and stuff later on, and especially in Calc 2. So, because in essence, integration goes backwards. So you have to actually remember to go backwards through the loop instead of forwards through the loop, which can become a little confusing. So, all right. So we've now got what sine of x is, and we've got what cosine of x is. What's the other trig function? Tangent. Let's find what's the derivative of tangent of x. How can we use what we already know to find this derivative? Yes. Yes. Yep. Tangent is sine of x over cosine of x. So now I can use what rule did we learn last week? We can use the quotient rule for this one. So remember, for the quotient rule, I have, I'll do n of x is sine of x. So n prime of x is cosine of x. And then we have d of x is cosine of x. So d prime of x is negative sine of x. I just use n and d for numerator and denominator. Because I couldn't use f because I already used f in the original problem, so I couldn't use f and g. Kinda. All right, so let's look at what was the derivative rule. I mean, what was the quotient rule, I should say.
Times G minus G prime times F.
All right, so we have cosine of x times cosine of x, because it's f prime, which is the top, n of n prime times the denominator, minus negative sine of x times sine of x over the denominator squared, cosine squared of x. So on the top, I have what? I have cosine squared x plus sine squared x, right? What does that equal?
1.
That's 1. That's Pythagorean identity. Cosine squared x plus sine squared x equals 1. So my f prime of x is now 1 over cosine squared x, which is what? Yes, secant squared x. So my derivative of tangent of x is secant squared x. All right, there's 3 more trig functions. What are the other 3 trig functions? Secant, cosecant, and cotangent. And they are all what? They're the reciprocals of the other one. So in essence, if I wanted to find my derivatives for each of those, I could use the quotient rule again, because I have something over something. The top is a 1, but it's still something. Okay? We're not going to do that. Here's your trig for the derivatives for these 6 trig functions. But we're not going to do it yet. I might have you do one of them later on. Out of them, the ones that you're going to see most often, obviously, are sine and cosine. You're going to see those a ton. You will see tangent and you will see secant. Okay? So those 4 are the ones you're going to see most often. All right? So those are the 4. If you're going to try to remember something, those are the 4 I would try to remember. Sine, cosine, tangent, and then secant. Those have a tendency to come up quite often, especially when you're doing some integrations. And if you look at like tangent and cotangent, tangent was 1 over cosine, cotangent's 1 over sine. Same concept. And the sine's different because the same concept of sine and cosine, the signs are different. And cosecant's actually just the opposite of secant. Secant, cosecant, tangent, cotangent. So they have some kind of relation to each other. All right, everybody got this table down? Okay. Make sure you write, because we're going to use this now for the rest of the class. So.
The rest, like going forward, gives me a lot of trig functions now.
No, so we're going to look at the chain rule and some other stuff, but now that we have the trig rules, instead of just doing basically like polynomials and stuff like that and those type of equations, we're going to add in more trig functions to them. So we're still going to be doing the product rule, still going to be doing the quotient rule, stuff like that. We're just now going to be using the trig rules with that, like this problem. All right, y equals sine of theta and cosine of theta. The theta is no different than an x, so don't freak out with the thetas. They're just a variable. You are going to see thetas quite often when you're dealing with trig functions because you're looking at angles. So if you want to write an x on your paper when you're writing it, that's fine. It doesn't change anything. All right, how do I find the derivative? Yeah, you have to use the product rule for this one. The answer is not cosine sine. Okay? You still have to do those other rules. This is a product. We still have to do that product. So I've got f of x is sine of x. So f prime of x is cosine of x. G of x is cosine of x. B prime of x is negative sine of x. Be careful. The number one thing you're going to screw up with the trig, especially sine and cosines, are your signs. All right, you're going to forget a sign here and there, so just be wary of that and look. It's really easy to go sine, cosine, cosine, sine, and forget that negative sign. All right, so it's the derivative of the first, so cosine theta times cosine theta plus negative sine theta sine theta. Remember, it's in essence the exact same as the quotient rule on the top, except it's plus instead of minus. So what do I got? No, we don't have one. Cosine squared theta minus sine squared theta, which is not 1. Cosine squared theta plus sine squared theta would be 1. Minus is not. So that's my answer. Huh?
Oh, we got a sheet last year of all the different, like the sine, cosine, like the trig function.
Yes. Oh, yes. Actually, I think it's at the back of your textbook too. If you had the actual textbook and not the online version of it. But yeah, that sheet's always very helpful. Yep, I did give it to the class last semester. All right, so yeah, that's really easy to go. Oh, cosine squared theta plus sine squared theta. Oh, 1. Really easy to do that. Just be careful.
Give us most of the points for that one. If we did that.
If you had wrote that and then put equals 1, I probably would give you most of the points. If you just wrote y theta equals 1, debatable. All right. All right, try this one. Do the spring problem. All right, so which rule am I using? Yeah. So n of x is secant of x. What's n prime of x?
Oh.
Okay. And then d of x is 1 plus tangent of x. So d prime of x is what? secant squared x. Because what's the derivative of 1? 0. All right, so now all those people who had 1 plus secant squared x, fix the rest of your problems. The derivative of 1 plus tangent x, the derivative of 1 is 0, so that's gone. Derivative of tangent x is secant squared x. So since you probably put 1 plus secant squared x, now you got to finish your problem again.
What if you did the quotient?
I just haven't done the quotient rule yet. Product rule?
Yeah.
What do you mean?
I separated the secant from the top. Changed it to multiplication.
So you did secant x, but you'd still have to do the quotient rule on the 1 over 1 plus tangent x. So that wouldn't necessarily help you. This lesson. All right. All right. So if we did the quotient rule, I have secant x tangent x times secant x minus secant squared x times secant x. Thank you for updating my ad block in the middle of class. All over 1 plus tangent x squared. Oh, you're right. I'm like, I was looking, I'm like, I know something's wrong here. This doesn't look right. There you go. That's better. All right. So let's clean this all up. All right. So if we look at this is where algebra really comes into play. It's like, how can you clean this up to make your life a little bit easier? It's pretty messy here. We're not going to deal with the bottom at all. Literally, the bottom is just going to stay like that. Okay. So do not try to foil that out and stuff like that. Just leave it like that. Unless at the end, after you've cleaned up your top, it's like, I can kind of do something with this. All right. I have a secant in both parts. So let's pull that out. So now I have tangent of x plus tangent squared x minus secant squared x. I took out that secant and that secant.
You can do that.
If I had, say, an A in both terms, could I pull the A out? Yeah. Same concept. As long as you have something similar in both terms, you can pull it out. This is where remembering your trig rules really comes into play and helps you out. Secant squared x is 1 plus tangent squared x. So there's a minus sign in front of that, because there's a minus sign in front of that. So that means that tangent x and that tangent x will cancel each other out. So my top is now just secant x tan x minus 1 over 1 plus tan x squared. Sometimes, like in this case, simplifying it down makes it look simpler, but it doesn't really help me get rid of anything else, especially on the bottom. Sometimes it will. Like if that ended up being tan x plus 1, I could cancel that out with something on the bottom. That's why you want to try to simplify them down as much as possible, because sometimes it does actually eliminate things and eliminate your problem down quite a bit.
We should remember our own trig rules.
Yep. Or at least have them easily accessible for you. Remember what I said on your test? If I use a rule on the review test, I will use that rule on the actual test. Okay, so if I'm using the rule on the review test and you can't remember it, I would write it on your next card so you have it on the test. Okay. Because there is a ton of identities. There was 2 pages of them that I gave my pre-calc class last semester. So there's a ton of identities. You're not going to you're not going to be able to remember them all. But being able to manipulate certain things is going to be very important. All right. We're going to come back to that. Actually, you know what? No. All right, do this one. Yeah. Remember, theta is just like x. So dying gun. I said you're dying gun.
Yeah. No, you can take these. Yeah, that's the inverse of the whole line of screen where I think that's the. Which rules should you use for this one?
Product. Because you have a product. If you were to distribute it first, you'd end up having two products, which would not probably make your life a lot easier. But yeah, you have to use the product rule for this one. So we have so that's the first one. Which, even though the book didn't do it, that equals that. You don't have to. It's not really going to make your problem like the simple at the end. It does make it a little easier to write things down, though. One less subtraction you have to deal with. So G prime of theta equals E theta times tangent theta minus theta plus E theta times tangent squared theta. So we can pull out our E theta and we get tangent squared theta plus tangent theta minus theta. And that's as far as you can go for that one. Or if you didn't change it, it'd have been secant squared theta minus 1 plus tangent theta minus theta. Both answers would have been correct in this case.
So why in this one do you not get rid of the constant one?
What do you mean, this one?
Yeah.
Because it's theta. What's the derivative of x?
Oh,
1. And the other one, it was the derivative of 1, which is 0. So that's the difference. All right. Let's do one more. You can blame him. He was the one who caused this problem. He asked me last class what happens if you do 3 of them. And I don't think I did 3 of them in the last class. So I figured I'd give you 3 of them this class. Can't factor, don't have addition.
Professor.
Yeah.
If there's 3, do you put 1 on the bottom?
No. You have to do your quotient rule twice, or your product rule twice. Yeah, just pick which one you want to use. So let's make this TE to the T. And N of T is cotangent of T. All right, I'm changing these to X's. I'm not writing all these T's. Yeah, that's just wrong. All right. So you could have broken up, like you could have put the E to the X on the second one if you wanted. It doesn't make a difference. All right. So now find me M prime of X and N prime of X. You just now have to do the product rule for that one. Not one, cotangent x. There. I pulled out the x and I didn't distribute. So if you were to distribute everything through, you'd have an e to the x on every term. So you can pull the e to the x out front and then just write the three terms that are left over. Nope. Because then I would have two of them. So you're fine. So yeah, if you distribute that, so you get e to the x. No, that's fine because I actually had one there originally. So if he spoke sooner, he might have caught me on something.
You have to do that. A term times t.
What do you mean?
What are we gonna do with that extra t at this code?
This one?
Top one, yeah, yeah.
That's cotangent of x. That's not an extra t. That's the function.
So, I don't know why I thought like t's.
Well, that's why I didn't want to use t. Yeah. Yeah. Okay. There is an actual reason a lot of times you will see t, especially in trig functions, as you're going to see in the next problem, is because t is typically representative of time. So there is a lot of problems that deal with time. So you will see the letter t used for that reason. Okay. So as in the next couple of problems we're going to see. But yes, my final answer is at the bottom. However, you can easily just change it to x's. That's fine. It's not going to change your answer. The only thing I will tell you is in future classes, because your teacher might care, is make sure you write your answer. And I know WebAssign will care. Make sure you write your answer in the original variables that the problem was in. So you'd want to write your answer with t's instead of x's. That's the final answer. Otherwise, you will most likely get it wrong in WebAssign. All right, let's look at some applications. So I know last semester in my pre-calculus, we did some of these problems. I don't know about any other class. So you had problems that looked like this. And you had to figure out the displacement equation. So in your pre-calc class, you actually would have had to figure out the 4 cosine t. Okay. So we don't want that. I'm going to give that to you here. What we want to find out though is the position is that I want to figure out what the velocity and the acceleration is of the spring. So how fast is it changing? So if I have my position, so if S equals the 4 cotangent t, and this is why they use t, because t is time, what is the velocity going to be? Oh, you're right, cosine. I had t's on the brain. What's the velocity of your position? Correct. It's S prime. So what's the derivative of 4 cosine t? -4 sine t. We do not have to do the product rule for this. Okay? Because 4 is a constant. And will be the derivative of 4. 0. So it cancels out anyway. What? Yep. Yep. This is why if you do calc-based physics, it's easier. Because you now have the answer. You don't have to do a whole bunch of algebra to get it. Yes. All right, so that's my velocity. What's my acceleration? It's the second derivative, which would be what? -4 cosine t.
And,
The jerk would be the third one, which would be 4 sine t. All right. So we have these. We can now figure out the maximums and minimums and all this other stuff. So when is the velocity? When is the maximum velocity? So if we want the maximum velocity, we're looking for the peak of negative sine of t, right? Or -4 sine of t. So your peak appears at where in sine of t? Just sine of t. Where's your peaks? Where's your peaks appear? Nope. That yes, the values are 1 and -1, but where on the x-axis, where do they occur? So 0 sine is 0, right? Pi over 2 sine is 1, right? Because we're looking at velocity. So pi over 2 sine is 1, correct? Yes. Pi sine is 0. 3 pi over 2 sine is -1. And then 2 pi sine is back to 0. Sine, not cosine. So since it's negative, that reverses, right? Let's look at the graph. No, because it's not a parabola.
Cosine squared, that did you do that? I remember there was a bunch of cosine.
All right, so I have yes, but then you still have to go backwards. So here's my -4 sine x. So its peak is at 3 pi over 2. So its max acceleration is when time equals 3 pi over 2. So what's the position of the function at that point? Where on the cosine curve do you think you'd have maximum acceleration? Now I figured I'd deal with physics. Might as well have fun. So there's your acceleration. That's the maximum maximum velocity, right? And your maximum velocity happens when you're right, because that's when it's right between the minimum and maximum points. That's where it has the maximum velocity. Because before that point, it's basically accelerating, and after that point, it's decelerating. So if we look at our concept, decelerating, accelerating. So you start to see that connection between. This is why, like I said, calc-based physics is nice because you can get those answers really quickly. now that you know your derivatives. I don't know if your algebra-based physics teacher will like you doing that, but you now have that answer. So it's what my calculus teacher told me, and it comes up with the right answer. All right. So do this problem for me. And actually, you really don't need the picture, so I'll just make that a little bigger. So I want the velocity and acceleration, and then I want to know the position, velocity, and acceleration at that time, and see if you can tell me the direction that it is moving. So my position equation is 8 sine t. Find the value. All right. So your velocity is 8 cosine t. Your acceleration is -8 sine t. All right. So what's sine of 2 pi over 3? What is it?
I got negative 8.
Okay, hold on. What's the, where we go that far?
Oh, what is
Square root of 3 over 2, right? All right, and then 1/2. Square root of 3 over 2. So this ends up being 4 square root of 3. And cosine of 2 pi over 3 is -1/2. So that's -4. And then -8 square root of 3 over 2 is -4 square root of 3.
I see it.
So which direction is the object moving at 2 pi over 3? To the right or to the left? So if we look at the object, that's equilibrium. So is it moving to the right or to the left? At 2 pi over 3. Why is it moving to the left? Velocity is negative. Yeah. So moving. Yeah. You could. The velocity tells you the direction. So it is moving to the left. Okay. All right. One more problem. Then I'm going to give you guys a couple problems just to try. before we leave. Write down this. You don't have to write down the whole problem. Just write down that. Okay. So this one's got a whole bunch of variables in it. Sometimes you're going to see, well, and this is just literally a formula. This is a formula for, what's this one? Dragging a object across by a rope with friction and the weight and everything else put in there.
This is the actual formula for that.
It should work for pretty much any of those, yeah. I believe it or not, I never took physics, so I was one of those very lucky students at my college allowed computer science to count as a lab class. So I took programming classes instead of having to take physics and chemistry or any of those actual lab classes, which was great. So this is, I'm going to guess the actual formula because basically the equations are there, so you can change them to find anything. So it's telling you to find the rate of change of F, which is the force, with respect to theta. So the only variable that we care about is theta. All other variables will be counted as constants. Okay? So when we're looking to do the derivative of this, the mu and the w will be considered constants. Okay?
This way?
So this is a quotient, right? So I've still got to do my quotient. So we've got my numerator is that. So my derivative of that is what? Yeah, it's a constant. Derivative is 0. There's no thetas there. There's no variables. That is a constant. My denominator because that's a constant, I do not have to do the product rule. That'd be just like if I put the number 5 there. So what is the derivative of sine theta? Cosine theta. So it's that cosine theta. What's the derivative of cosine theta? What's minus sine theta? So it's one of those ones that I know it looks confusing because they're there and you see variables like they're variables. We're not looking at them as variables. Okay, those are ones that we're going to plug an actual number into. So because we're going to plug an actual number into and that's not going to change over time, that would be a static value. So mu is the coefficient of friction for any object. That coefficient of friction stays the same. The weight of the object would stay the same. So if they did change and you had multiple variables that would change, which can happen, you'd be doing multivariable calculus, which is Calc 3. So, all right, or differential equations, which deals with multiple variables. So, but here, Calc 1 and Calc 2, you're dealing with just one variable. So let's set up my quotient function. So I have 0 times, I don't even care, because 0 times anything is 0, so why waste my time writing it down?
Yeah, keep getting confused. W.
Yeah.
That's what we have.
And then we have cosine theta minus sine theta times mu w. And that's all over sine theta plus cosine theta squared. Which reduces down to that. When you clean it up, that's what you get.
Mu in calculus just means any number.
Well, mu can be, these are just variables. It can technically be anything. Typically, that's the symbol you see for mean when you're dealing with statistics. Apparently, in this problem, that's the coefficient of friction. So maybe I'm going to check what's the. Yep, that is the variable in physics used for the coefficient of friction. So. All right. So so we've got our derivative now. The second part of the question says, when is this rate of change equal to 0? So how would I want to know when this equals 0. Huh? No, I know when it exactly equals 0. That would work if my theta was 0. I want to know what theta is going to give me 0. So do I care about the bottom? No. First of all, the bottom can't be 0. All right. So if the bottom comes out to be 0, it doesn't exist. So that's, and if you're looking at these two, sine and cosine will never both be 0 at the same time. So therefore, that bottom can never be 0. Okay. Unless the coefficient of friction is 0, in which case it can be, but that would be weird. So we're going to assume this can't be 0. So the only thing I'm looking at is the top. Now, this is a constant, right? Those are going to be given to us. The coefficient of friction should not be 0. The weight should not be 0. If they are, then there's no point in doing this problem. So the only thing that I have to worry about is really what's inside this parenthesis here. So I'm just looking at sine of theta minus mu cosine of theta equals 0. All right, so what would we like to try to solve this?
You just pick them from basic variables, like regular algebra.
Except they're cosine and sine, so they're not just a variable. So this is where, like, if this was a parabola or this was a polynomial and those type of things, get it all to one side, factor, get your zeros, those type of things. When you're dealing with trig functions, it becomes a little messier. And actually, in this problem, the only thing that's really annoying is that value right there. So really, if we can kind of get that by itself, this might be a little more helpful. So let's move the cosine over. And then let's divide by cosine. Because now I have tangent of theta equals mu. And if I want theta, how do I get rid of tangent? Nope. Nope. How do I get rid of my trig functions? How do I get rid of anything? How do you get rid of addition? Subtraction. How do you get rid of multiplication? Why? Because they're considered what? Nope. Not reciprocals. Starts with an I. Inverse functions. The inverse of addition is subtraction. The inverse of multiplication is division. The inverse of squaring is the square root. What is the inverse of a trig function? Arctan or inverse tangent. So tan negative 1 of mu equals theta. Or arctan. Those are the same thing. So in the arctangent of mu, whatever that happens to be, because I don't know what it is in this case, because it changes, equals theta, that's when my force will be 0.
There's some sort of angle identity for sine minus cosine theta.
No. Only squared. All right. Let's give you guys a problem to try. All right, I'll give you a choice. Do you want 2 easier ones or 1 hard one?
One hard.
1 hard one? Okay. All right, here you go. Oh, did I not? Sorry. There you go. I was really thinking really hard to go with that hard problem. I just totally didn't switch it over. I had 2 screens up so I could actually see, like, go ahead and write stuff down, and I had it on that screen, but not the one that I was sharing with you. I was clearing up my text messages.
And this is the hard one.
Well, it's a quotient rule one, so
Professor, can we make that G an M instead?
you can make it whatever you want. I don't care. You can make it M of X. I don't care. So you can use F and G.
Like, I automatically started.
Like I said, though, just be aware that I know for a fact WebAssign will mark you wrong if you have the wrong variable. So, I don't know actually. I know Alex would, but I don't know about WebAssign. Correct. It doesn't send you back. This is true. Alex makes you learn it.
Right? The derivative.
The derivative of x is 1. Yes, the derivative of your numerator is not 0. It is 1. Nathan. Here? No? I have your pack. Kaylee? Mary. I give you the Huh? Yeah. And then all right, let me work out the actual problem inside here.
Probably not the answer. Secret X, stage X. What do you got?
Well, I kept taking out secant, and it kept kind of boils down to 1 plus 10, which is secant squared x, which means
If it's 1 plus tangent squared x, yes, not 1 plus tangent x. All right, so that should be your first step after you've done your derivatives. So The derivative of the top is 1, derivative of the bottom is secant tangent plus secant squared x. Okay, that's the first step. All right.
So you're ready to have.
So now let's work at simplifying. There was a couple things they did between here and here. They didn't change anything in the first one, but the second one, I have a secant in both of them. So they pulled that secant. So now, if you look, I have secant z, tangent z, secant z, which is the same thing. And both of them. So I can pull that out. And I'm left with the 1 minus z secant z. The reason why, so if you remember the other one, we did a whole bunch of simplification. We got down to the end, but it really didn't do anything to the problem. In this one, I can now cancel that with that. So that's my final answer. So you can't, that's the reason why we went through all those steps to simplify down, because that actually does remove stuff from the actual final problem. So I end up with 1 minus z secant z over secant z plus tangent z. So you can see, I didn't hear any grumbles when this step happened, which means pretty much everybody is able to do the actual calculus, the actual derivatives, and the actual quotient rule, which is awesome. You learned what I taught you. Everybody, where I started hearing the grumbling was the algebra and the trig simplification stuff, breaking things down. All right, which is what I told you at the beginning of the class, which was going to cause you trouble. So, you know your calculus, which is awesome. You just got to get better practice at simplifying down the, especially the trig identities. Actually, this one really wasn't trig. This was just algebra, breaking things down. So, all right. Chain rule on Wednesday. I don't think it's that hard. The chain rule is not that hard. Actually, out of all the rules, I think the quotient rule is probably the most complicated, just because there's a bunch of parts with the fractions and stuff. Chain rule is typically not too bad.